Yeah, I'd like to begin by thanking the organisers for the invitation to speak at this conference. And also say, I always forget to say this, so I want to sort of pause and say it. This is joint work with Gavin Brown. I missed him out on more than one occasion doing this talk. I want to also begin by apologising for my title, because I realised it was maybe sort of unnecessarily intimidating. Because, let's be honest, the last talk of the day is not really the time you want to be told about A infinity structures. And so I sort of successfully managed to purge my talk mostly of that, you'll be pleased to know. And so I'm just going to sort of score this out, except it'll come right at the end. But really it's a little bit there as a sop to the fact this is a derived workshop, so I felt derived should be in the title. Somehow it's there, but it's somehow not there at the same time. Okay, so my motivation. And there's two sort of separate, well, maybe more than two, but there's some separate motivation for this problem. I just want to outline them both. So the first sort of genre of motivation for this is around very sort of easy to state questions about curves in threefolds. So this kind of comes under the banner of classification and contractibility. So suppose I have some reasonable, let's say smooth. So X is smooth. It can be projective if you want, that doesn't particularly matter. Let's just say it's three-dimensional. And I'll work over the complex numbers, although you'll be pleased to know that the main A infinity stuff later doesn't need that assumption. So inside this threefold variety, I'm just going to assume I have some sort of bunch of rational curves. But that's last typing. Yeah, bunch rational curves. So I have a collection, a bouquet of rational curves. So each of these CIs is isomorphic to P. And so what sort of questions do we want to ask? And so the first question is, what's the order? Well, I'll do the order here. It's classification. What is the minimum amount of information so C is going to be the union of these curves. I'll move my board up. I appreciate the fact I can't see that. Better. The minimum amount of information needed in order to recover the safe formal or suitably local neighbourhood of C. So say if you wanted to go sort of suitably locally, if you're quite happy going to formal schemes or analytic spaces or all that jazz, if you're quite happy doing that, you could sort of draw some sort of tubular neighbourhood around these curves.
Do you assume that C has arithmetic genus 0?
I can't hear you.
Do you assume that C is also like arithmetic genus 0?
At the moment, it's on the individual curves. On the individual curves. Right at the very end, there'll be something on it. If I get there, which I probably won't. So yeah, in particular, I am not assuming on the formal fiber H1 of the structure sheet is 0. Yeah. Sometimes it happens, sometimes it doesn't. Okay. And so, well, the question. And so, in many situations, which I'm not going to talk about today, this is somehow now known, that at least for reasonable curves that contract or something like this, the classification is at least as bad as noncommutative deformation theory. And so, you might hope that something like this is going to be true in general. And one of the reasons I'm doing what I'm doing in my results is partly to probe this more general question. How general, so what sort of deformation theory do you need to actually recover this problem? And it's clear you need some form of structure. It's clear at this point that sort of numerical or metric invariants aren't going to cut the mustard. You usually do need some sort of structure, sort of control, or some sort of isomorphism class or derived equivalence class to control this. So question 2, which really is the motivation today, which is contractibility. Contractibility. What structure detects whether C and X contracts suitably locally? So again, I could be doing that on a formal scheme or some sort of reasonable algebraic space. So there's I mean, if you zoom in a little bit to the curve, you're not expecting a global answer. That'd be quite hard because that doesn't exist for surfaces. But you'd expect some sort of local answer again because that exists for surfaces. And by contract, before someone shouts at me, I'm going to mean today, I don't always mean this, but in my sort of suitably local neighborhood, U, I'm going to, there's a morphism. So I take away the curve, there's a morphism U to G con, such projected by rational, such that away from a point, the curve is contracted. So I'm sort of suitably locally contracting it at that point. The curves go to the point. Okay. So, and question 3 is really just a sop to the fact this is a derived workshop. Is does the derived category answer either question 1 or 2? Does dB X C? And if you believe the answer to that is yes, then it somehow tells you the only thing the answer can be, but it's not entirely obvious that it does. So that's part of the problem.
So, do you say that local contractibility does not imply the global one?
Yeah, it's even in surfaces. If you take a bunch of reasonable curves in a surface, like Artin's contractibility criteria, which I'm about to come to, says that suitably locally you can contract the curves. It makes no statement that globally you can contract them. So you can globally contract -1 curves, for example. When you start contracting other curves, it's a bit more delicate. Yeah. So, okay. So the key test today is you can make grand claims all we want, but the key test today is a single curve. So I'm inside some reasonable X. I have my single curve C, and I'm going to assume some sort of Crepant condition on C. But I'm going to come back to that later. Okay, so this gives rise to an object which we call E, which is the structure sheaf of the curve, which is the coherent sheaf. Okay, so without any technology, there's a quick and dirty way of deforming this. So, in some sense, what I want you today to do is view this as a black box, right? You input a curve, and out pops an algebra. Very black box. But if I present it like that, people get upset because they want to know how that's done, right? And here I'm going to present you for non-commutative definition, and you're going to complain to me that you didn't actually want to know how it's done afterwards, right? So I'm aware of this, but so this part of the board you can roundly ignore afterwards. But I'm just going to explain how you go about obtaining this algebra. So there's a deformation functor, E, which goes from what's called art1 to sets. So the category of sets, that's fine. Art1 is basically finite dimensional local C algebras. But that's not enough. You need, with extra assumptions, e.g. all simples one-dimensional. So if you're an algebraist, think of basic algebra, that's kind of cool, and they've got to be augmented. There's some various technical assumptions, but basically all local C algebras. And in particular, the non-commutative comes from the fact I'm not assuming it's commutative. Well, not necessarily commutative. Okay, so how am I going to deform my curve over such an object? Well, I take my test object R and I have a functor, so I have to map every object in this category to some objects in this category, so I have to map it to a set. Whew. And so what do you do? Well, you want to say, what is the deformation of the curve? Well, first of all, somehow morally, it's a sheaf on X cross spec R. Yeah. But the slight issue is that spec R doesn't exist because R is not commutative. Yeah. So what does the sheaf on X cross spec R mean? Is, well, it's going to be a sheaf F on X together with a homomorphism from R that's endomorphism. The data is going to be of a sheaf and a homomorphism. So this is somehow morally sheaf on X cross spec R. You want to have some idea it's somehow same size, so this is somehow the flatness condition, and that's a homological condition, so that does make sense. There is a functor that looks like this, and that's going to be exact. And there's also the thing you have to recover the curve of the zero fiber to get the curve you started with. As that's saying, in this terms, you should be able to recover your original sheaf E when you pass the zero fiber, because that doesn't make sense. But you can't do this, which is classically what the zero fiber is. And of course, there's a choice and isomorphism, so you have to record that choice, which is a bit annoying. And there's an equivalence relation that you really don't want to know about, but it's quite natural. And so that's your deformation functor. And this, what I'm trying to say is, it's not that bad. It's just basically you take the classical thing, you have to reinterpret it a bit, and you get some answer.
Is X part of the information or?
F is so you yeah.
X.
Well, it's going to be a sheaf on X, right? X
So you pick the X and do this story.
Well, it's not going to matter. So there's theorems that tell you that it doesn't matter. You can be an X or any local neighborhoods or things like this. But so this is why I go into the formal neighborhoods. And essentially, that's, I mean, morally, deformations are only going to see a formal neighborhood anyway, because it's a formal object. But you're right, it's not particularly interesting. Good. And so, what do I want to say about this? It exists, and it's known by various people, Liddell, Ericsson, well, lots of people, Kawamata, myself and Will in various cases. This was called the pro-representing hull. There exists an algebra which we call lambda def, the deformation algebra, such that the Hons art 1 lambda def is basically this functor. It's not quite an isomorphism, but it is up to some axioms. So it's isomorphism with tangent spaces and various axioms are held. So it's I'll just put in brackets are almost an isomorphism. If you don't want to know the term. And this is unique up to non-unique isomorphism. That doesn't matter, at least it's unique. And so you should view this as a machine. You input a curve. Sorry, I'll move it up again. Sorry. Better? Not really. You input a curve, out pops an algebra. That's all you need to do. And there's some reasonably canonical ways to do it. And you'll be pleased to know you can do it with the infinity structures if you want to. But because this is 4:30, the last talk of the day, we're going to do it very nicely. And this is important, actually, there's a technical point here. If you want to deform a characteristic P, you should use the naive definition. If you want to deform a characteristic 0, you have a choice, you can use the naive or the infinity version. Okay, and so the conjecture which we're calling threefold Artin. So there exists this contraction. So the curves contract suitably locally, which I'm not going to try to explain. So you see, so the curves contract to a point like this picture is beautifully illustrating to you here. If and only if the dimension of this algebra is finite. So conjectures are easy to state. I want to give you 3 reasons, first of all, why you might like this conjecture. And I'm going to try to give you 3 reasons why you might believe the conjecture. So one of the reasons that you might like it is that somehow you've got curves and surfaces. The technology does apply to surfaces too. I'm speaking that under the rug. But if you want to control contractibility of curves, is one of the most fundamental things you can do with curves inside varieties. It's a very fundamental object here. And similarly, asking whether an algebra is finite dimensional again is a sort of fundamental sort of thing you can do in algebras. And one of the reasons I like the conjecture is somehow telling you that these 2 things really do on the nose coincide. The second reason that you might like this conjecture is that it's true for surfaces. So let me tell you how to interpret this. A reinterpretation of Artin's work. Right? So if you have a bunch of Crepant curves in a surface, so it's a bunch of -2 curves in the surface, Artin tells you that they contract if and only if they're in sort of ADE formation. What is the deformation algebra if I apply this technology to surfaces? Well, that's the pre-projective algebra. And it's a well-known theorem that pre-projective algebra is finite dimensional if and only if you're ADE. So the theorem is true, or the conjecture is true for surfaces, but in a very non-direct way. And so how I interpret this is I think this is a sort of 3-dimensional lift on the algebraic side of what, on the algebraic side, it's like, should be viewed as sort of 3-dimensional pre-projective algebras. And on this side, it's telling you that somehow the combinatorics of Artin for surfaces aren't enough. And it's what the philosophy is the algebra structure that's saving you. The algebra structure replaces the combinatorics.
Mike,
Yeah.
sorry, so in the definition of this deformation functor, so your lambda def is a priori what?
A priori, it's in the completion of this category. Okay. So it's a pro-Artinian sort of object. So I'll give you some examples in just a moment. Yeah.
Because it was confusing that you write you have homes in Earth 1.
Yeah, oh, sorry, yeah, sorry, there's some pro category. Yes, sorry, yes, yeah, sorry, yes, you're right. But ultimately, yeah, we can come back to that. It's some extension category. You're right.
In Fermat's view of the self-extensions, right? So you can do the self-extensions of those 3. And then lambda def being finite-dimensional means that they terminate or something.
Yes.
It's exactly the same.
And so there's another reason you might like this before I go to believe it. The last one is, again, for surfaces, it's a sort of, I think it's one more personal reason actually. This is telling you that if this is true, which I'm going to try to convince you, it basically is, but kind of isn't. It's telling you to lift the original work from Artin's 1962, right? That's his early part of his career. And if you want to lift Artin's early work of his career, very much in algebraic geometry, it's telling you, if you want to lift that from surfaces to threefolds, you actually need the non-commutative algebraic geometry technology. And so you actually need Artin's work from the latter part of his career. So why you should believe this? That way's no. Yep. That's no with much greater generality. That's by myself and Will many years ago. And the converse, the only open case is -3, curves. Is when the normal bundle of C and X is, I can say this is for Crepant curves. So there's some sort of version of this. When the normal bundle is -3, 1. And that's due to the Udo and Karen, and then myself and Gavin. They do an algebraic version, we do an analytic version. But the only open case of the conjecture is in the normal bundle is -3, 1. And so in particular, and that motivates us to wonder, for -3, 1 curves, what is this algebra, right? And so that's the sort of main point of the rest of my talk. And so that's sort of the motivating this answer. Okay. This is abysmal time management. Anyway, so the upshot is going to be, because I'm clearly not going to get to my talk, the upshot is going to be, in this case here, that basically, again, it's going to be true apart from a very, very tight region. So it's going to be the sort of the conclusion of the talk is going to be that the conjecture is still a conjecture, but in practice, if you actually find a curve in the threefold, the conjecture is going to be true, right? And so for all intents, so you're going to be very unlucky if it's going to be interesting if it's false, because it's going to be false in a very, very, very tight region. So I'm going to skip over the second bit of motivation and get going. So this is 3. So if you want to describe what this object is, deformation theory is not often criticized for being overly explicit. So if you want to describe what this object is, you're going to have some idea of what you want the answer to be before you start, right? There's no, you don't dive into the infinity calculation hoping for the best, right? You try to formulate what you think the answer might be first, and then you go in. And so I need to tell you what the answer is going to be before I tell you what the answer is. And this is what we're calling free necklace polynomials. And the whole point of this section, which is incredibly elementary, is the fact that the cyclic group of order n is much, much, much smaller than the symmetric group of order n. And that's all this is going to tell you in a very sort of crazy way. Okay, so I need 2 colors, orange and white. So I want a necklace. I want J beads to be that color, and I want K beads to be, that's probably a bead, was it? Is that bead on the back, or do you want me to change the color? Okay, good. Good, and I want to look at the set of necklaces. Nec J plus K is the set of necklaces with J plus K beads. And so, e.g., J equals 4, K equals 2, 2, 3, 4, 5, 6. There is a necklace. I'm allowing myself some only colors. I want J of these. Comma. And so there's an example of a necklace. Looks like that. So on this set, there's this obvious action by rotation. I can rotate a necklace with a certain number of beads in it, and it's going to be the same necklace with the same number of beads in it. That's right. So on net JK, there's an action by rotation by Z of J plus K. And then I forget the fact there's a necklace and the fact there's just a bunch of beads. The symmetric group is acting as well. And you should be more upset by that action because it's somehow, you're forgetting the fact it's a necklace. That's the point. So you should be pretty chilled about this one. You should be unhappy with this one. And this translates later that you should be unhappy with commutative deformation theory. The non-commutative deformation is much more natural. Good. And so in my example, and so there are orbits. Yep. So there's lots of orbits here. And there's a single orbit here. And so again, if I do my example, j equals 4, k equals 2, which you can see I'm not doing live for deliberate reasons. There are 3 orbits of this action. And so what are they? 1, 2, 3, 4. 1, 2, 3, skip. 4. 1, 2, skip. 3, 4. I can colour that once if I want to. It's not that important. So this is quite elementary, I hope. And let's count how many things are in each of these orbits. So the number in the orbit, well, I can rotate this 6 times and I get a different necklace each time. There's 6 things in this orbit. I can rotate this 6 times, the same here, 6. But as soon as I rotate this 3 times, I get back to where I started. There's only 3 things in this orbit. Good. And I want to do something just a little bit cheeky. I want to start at this vertex and read round this way. And every time I see a white, I'm going to write X. And every time I see orange, I'm going to write Y. So it's X, 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 Y, Y. Here it's going to be X, 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 Y, X, Y. Here it's going to be X, X, Y, X. So this is just a formal string of things which is going to be inside the free algebra. Good. And the definition, the main gadget at the top, the free necklace polynomial n jk is in 2 variables x and y, and it's the sum over the orbits m of this action acting on the necklace of the number of things in the orbit over the number of things in the group times this poly of the monomial, which is going to be, which is either this, depending which orbit. So that's the poly m. That, or that. So just for calibration, the necklace polynomial 4, 2, which is my example, well, it's 6 divided by the number of things in the group, which is 6 times this. That's x4 y squared, plus the number of things in this orbit, which is 6, divided by the number of things in the group, which is 6. So you get 1 times the next thing, which is x cubed y, xy. Then you get the crazy coefficient, and this is 3 divided by 6, which is a half. So it's a half of x squared y And there is a what's called a free necklace polynomial. Okay. And then, so I think basically what I'm trying to convince you is this is all very, very natural, very trivial, really. The coefficients are a bit delicate, right? It's not the first thing you might guess. And so then the definition, the periodization, take n to k and commute the variables. And so you view this, so the free, this necklace polynomial is in the free algebra, and say, okay, pretend x and y commute, and just view it inside the polynomial. And then the point is that the periodization is always 1 over j plus k times just the number of necklaces, which is that, times x to the j plus. So what's the point I'm making here? I'm not torturing you for no reason, so you think. But the point is here is that going from here to here loses a massive amount of information. Just a huge amount of data is lost going from here to here. That's point number one. Yep. Like a huge, massive amount, I want to emphasize this, huge amount of data is lost. And the second thing is that even if you didn't know any of this nonsense, right, and the symmetric group is acting on these things, right, now this is a pretty natural coefficient. There's a sort of natural thing here, no x to j y, that's pretty cool. But I don't think you'd have guessed that coefficient as a sort of natural thing all by itself, right? The symmetric group sort of is acting. It's sort of just come out of the noncommutative stuff, but by itself is not particularly justified. It's a bit vague, but it's still quite a nice expression. But you wouldn't have got out of bed in the morning. I think that's the expression that's going to solve this problem. But this is a little bit more, I don't know, nice. Okay, so then I can do the results.
Can I just, the original guy is supposed to live in the, like, 880 or something, right, the commentators there.
Yeah, so you have choice of how you do this, but I haven't told you how you differentiate yet. And so it's only defined up the commentators. It's the orbits. You're taking representatives of the orbits.
In particular, the breaking symmetry is done.
Okay, results. And so I do promise my tutorials and my talk are related. I'm not just telling you random facts of mathematics to fill up the last hour. So, what the purpose of the first part of the talk is that we're interested in -3, 1 curves. We want to probe conjectures and structure for -3, 1 curves. Yeah? So I'm going to have to construct for you now -3, 1 curves. So the question is, how do you do that? How do you construct a -3, 1 curve? And so, of course, what you do for this is you consult the string theory literature, because the string theorists were doing this back in the early 2000s. So the string theory so I'll give you some names. So Ferrari is the person that simplifies this the most, and Curto-Morrison as well. And just back further to Leifer and various other people. And so, what's the game? So the game is we're going to construct something, but it's up to choice. You're going to choose stuff, and I'm going to construct a -3, 1 curve. So you get to choose, so really it's you choosing, it's not me. You get to choose some scalars. So it's finite number of scalars in the complex numbers. I'm pretty sure you could do that. And so, but I don't want you to label them 1 up to n. No. I want you to label them in a mildly crazy way. And so I want to think of them as just some scalars. I'm just giving you a rather bizarre inducing set. It's not terribly, just confuse myself immensely now. 3, 0, that's the point. 3, 1, 1, 2, 0, 3. And so I want to think of your finitely many things as in this triangle where most of the things are 0, but you're going to tell me n spots where you're going to put non-zero numbers in. Yeah. So again, there's really a choice. Well, you can think of it as a choice of infinitely many things, most of which are 0. If you wanted to be that person, you can choose them all to be non-zero, but you have to work with formal schemes. And so we're just doing this finite number so the top is nice and calm. But you get to choose this number of scalars. And so from that, I'm going to glue, to get from that data, I'm going to glue a curve. It's like a cultural exchange program. Right, let's do this. So if you're happy sort of zooming in, or going to some sort of formal neighborhood, you're going to happy to be at least suitably local. My two patches are just going to be affine space. Let me get this right. So inside X, I have my curve, at least suitably locally, kind of locally, they're going to roughly look like A3s. Kind of. And so I'm going to glue two copies of A3, one in coordinates X, Y1, Y2, and I'm going to glue them with another copy of A3 in coordinates I'm never going to tell you by X, Y1, and Y2. Whenever X is non-zero, glues with X inverse, X cubed Y1 plus some perturbation term, which is where the scalars enter. So, not the first thing you'd write down, but it's somehow believable this is a reasonable thing to do. So if I completely ignore the fact of these scalars, what have I written down here? This is the glue of the kind of very free -3, 1 curve. So there's the number 3 here is important, and number 1's here. Yep. So if all the scalars are 0, this is just a total space. OP1 -3 plus OP1 1. And that curve doesn't contract. So what you're doing is you're putting in this perturbation term, and you're hoping that makes it better. Yeah. Unclear it makes it better, but you're hoping that improves the properties of this curve. And there's a lemma, Ferrari, which is actually a lovely proof. So if the sort of quadratic terms are 0, so that holds if and only if the normal bundle of the curve is OP1. And if they're not 0, that's either -2, 0 curve or a -1, -1 curve, and we know when it's fault. The point is that a lot of the time, this is a really good way of getting -3, 1 curves, right? You choose your scalars, as long as the top row is 0, you're happy, you build yourself a -3, 1. Good. And so, again, why morally is that sort of expected? You're taking a -3, 1 curve, you're perturbing, you're putting some perturbation in, and you're hoping that can only improve the situation. Right? And what does improve mean? It's going to be, it's a -3, 1 curve or better. And better would be a -2, 0 curve or a -1, -1 curve. And that actually corresponds to this case when this is not 0. Okay, and so the theorem is that for this, let's actually see what C is, yeah, very good. And so my P1, you can see I've got a P1 sort of in here. Yeah. And so I do have a P1 sitting inside my curve. And for this curve, P1, inside this sort of neighborhood X I'm sort of giving you, the deformation algebra is given very explicitly in terms of free necklace polynomial. It's given as, well, it's the power series ring in 2 variables, that's expected from deformation theory because of the situation, modulo the derivatives of some W, which I have to construct for you. where W is the polynomial jk times the net polynomial. So there's a closed formula for what this deformation algebra is. And so just say, there's technical points which you can ignore. This just means the closure of the ideal. And this means formal power series. You won't lose much in your head if you just ignore the fact that the formula is there because the free algebra. The result's false for the free algebra. But we don't worry about that. You need the power series rings for the theorem to be true, but for most intuition purposes, you don't need it. So there's a closed formula for what this is. And I'll give you some examples in just a moment. But the corollary which we really like. The corollary we get out is this 1970s theorem of Namba. And so in this paper, this was pre-growth and deformation theory. And so this was proved using actual complex analysis, like really sort of quite hardcore complex analysis. And so Namba's sort of paper, which is also when Katz explained this in the 90s, is that the commutative deformations of C and X are given by, well, formally, if the non-commutative deformations have got some answer, the commutative ones I just take the reorganization are pro-represented by the reorganization of this algebra, which is C xy modulo the commutator of WR, WY, WR, where WR is equal to this kind of crazy sum jk over j plus k to j plus k, k, x to j. And for about 9 years, myself and Gavin were puzzling over this theorem. Like, how would you ever guess this coefficient? How would you ever guess that the coefficient of the reorganization, the commutative deformations are given by this object? Why is this the correct coefficient of the commutative deformations? And the answer is, actually, it's easier to compute the non-commutative one. And when you go from here to here, this just pops out sort of naturally. So there's a few things to say about this. How does it have? 15 minutes. So I was going to give you some examples, because that may or may not help. All a bit unclear. So what's the upshot? Upshot is that we now have presentations of these things, and we're going to test conjectures. Like, when is this finite dimensional? That's a testable thing on computer algebra. And so in particular, when you're building -3,1 curves, if you stare at the glue, it's really, really hard to sort of know much about the geometry. So even just tweaking this just mildly, it's really hard to know what the intuition is for this. But when you tweak non-commutative algebras, they can go from being finite dimensional to be horribly infinite very, very, very quickly.
Do we know that every -3,1 curve has a formal neighborhood?
No, we do not. So it's we got a heuristic for why it's true and the heuristic for why it's false. So the string theorists don't make any claims either way on this. Actually, they're a bit sort of on the fence. I suspect the answer is maybe not. Can I give you maybe a little bit of heuristic? So the other motivation, which I didn't tell you for this talk, is that if you take an arbitrary quiver with potential, can you construct a geometric model of it? Yep. And so here, what this corollary is telling you, if I take any commutative potential, any commutative polynomial at all, anyone, well, of course, I can choose, I can get lambdas out of this and build your -3,1 curve. And so this corollary tells you that for absolutely any commutative polynomial, you can build a geometric model where the commutative deformations recover that. And so one of the motivations is the same non-commutative thing. So I take an arbitrary potential, non-commutative potential, can I build a -3,1 curve that realizes it? Okay. And this is telling you probably maybe not, right? So these are because this recovers absolutely all commutative polynomials, right? Absolutely all of them. Where this really doesn't obtain all non-commutative polynomials, right? And so, and that's sort of giving you a hint that maybe actually the answer is doesn't cover all of them. That'd be a sort of heuristic, because there might be other ones, and we've got other deformation algorithms which we can't build. So it depends on other conjectures you might think. But the downside is the conjecture. The reason why you might think it's true is that these objects are not changed on the analytic change in coordinates. So if you take one of these and analytically change coordinates, it's no longer a necklace column. And so in particular, you can't really square that, so it's very difficult to have an intuition. Yeah, I don't know if that's answering your question. I think the answer is probably no, but maybe. Yeah.
My answer is, so just to understand, so assume you have a curve you wish to contract.
Yeah.
So how do you get these coefficients lambdas? So what do you do?
So if you have a contracting one, or you have a
No, if you have a rational curve which is suspected to be contracted.
So if you analytically you complete along the curve, you don't get A3s, but you get some sort of where does the completion go? You get some sort of particularly locally, you get two patches that look roughly like that. Right? Two of them, and they glue together. And in that glue, the question that R is asking is that can you absolutely make sure that in that glue you can analytically change coordinates here and here to make the glue look like that? And that's not known. But this is also just a huge class. I should also say, I haven't said, this class contains all known threefold flops, all known real contractions occur. And there isn't a -3 curve that's known that isn't in this class. That doesn't help your question though, because analytic changing coordinates are pretty grim. And so we've taken off the completion, just gone Zariski local as the top, but really you're working in this sort of formal speed.
The finite dimensional is the closed condition under changing this W.
So in the sort of variety of all algebras, the problem is that most algebras are semi-simple, right? So if you choose an algebra that's semi-simple, well, it's sort of a slight issue in this sort of whole conversation. But I don't know the answer to your question. It depends on closing what, because the thing that comes out of the appendix with Gavin that proves one of the dilemmas that's no longer there is that Jacobi algebras have different properties than general algebras. It's actually very easy for a general algebra to be finite dimensional, but it's really hard for a Jacobi algebra to be finite dimensional. Another reason you might expect the conjecture is true that there's basically none of each. That actually contractible curves are so hard, there's basically none of them, and the Jacobi algebra is being finite dimensional so hard, there's basically none of them, and they can occur. I'm not answering your question. It's open. It depends on which class of algebras you want that to be. If you're inside Jacobi algebra, it's probably be nice to know algebra, probably not. Okay. End of rant. Good. And then that's a question I can rant at before I go on to the next one. So I want to say a little bit about technical. How we do this is we've known this answer for about 5 years. Actually, we knew this for a long time. We tested it to death on computer algebra. But somehow the philosophy was that if you want to get this result out, it's actually easier to get this result. That's the sort of the philosophy. And actually, you keep on going. And this is actually corollary to something else. You describe the derived deformation theory, and everything else flows out of it. That's what you actually do. And so the technique is that this curve, and this curve gives you some R-Holm DGA, and all you have to do is compute the infinity middle model of that DGA. So the technique is that OC is a curve in coherent sheaves. So it has and coherent sheaves with derived category coherent sheaves, it's got DG enhancements, right? And so you just form the endomorphism DGA. We're just going to call R-Holm of OC of OC. It's a bit cheeky, I know. People in the know. And all you need to do is compute the full A infinity structure, all higher products on this DGA. And so it relates back to the opening motivation. Does the derived category know about these problems? And the answer is resounding kind of, right? So, so people like Paulus, we actually use Stellari's results, that, you know, this X is quasi-compact and separated, so basically any DG model you can think of will be quasi-isomorphic to all the others, right? And so all you have to do, it's not, I mean, this is not just us, this is not a secret, right? This is all you have to do. The problem is like this step at the end, like how you calculate the infinity structure. And so, of course, there's many, many DGAs you can choose. They're all quasi-isomorphic, but some are slightly easier to compute than others. And so really the technique is that we're going to use check enhancement. Maybe I'll write this down. Check.
You write down the universal function?
For the deformation theory of the
lambda depth.
Well, what do you mean by write down, right? It's a quasi-coherent sheaf in general because it's some sort of limit of coherent sheaves, but you're only on the formal thing. I mean, it's a sequence of universal extensions, but we don't have any better description than that. So is that your question, or?
I mean, since equation of lambda depth are so closely related.
Oh, sure.
It seems plausible that we could just.
But that's how Namba did it, right? I mean, in the sort of classical deformation theory sense, you have some sort of reasonable space. The Kuranashi space, I forget the language. Yeah. But this whole point actually is that, in some sense, you know, we do sort of balk at doing these infinity calculations, but it's just linear algebra, right? You choose a basis of something, you mess around a wee bit. It's all linear algebra, as it somehow. That, strictly speaking, is easier than complex analysis, right? Modulo indices, other things. Can I just say quickly, so the key is that we use the check enhancement. And why would that be a good idea? And it's a good idea because you've only got 2 open charts, right? If you had 1 million open charts, this would not be a good enhancement to take. This is 2 open charts, so the DG algebra is actually quite small. You get the DG algebra is somehow small. And the second key, this is the sort of novelty we realize, is that actually there's a universal there's a locally free resolution that works in all cases. It exists as sort of universal, but it always exists. Well, it's just a locally free resolution. Uniform is probably better. Zero goes to E3, goes to E2, E1. So this is what this is why you can prove a theorem in general, is that there's a locally free resolution where we know these matrices in all cases somehow. So we know the matrices of local free resolution, and we just go ahead and we just implement category. And so the theorem, which I will just state very, very roughly, because I appreciate this is sort of 5:30 in the afternoon, is actually we compute every single infinity product on the DG. So we know all our multiplications on all of these. In the and in some sense, it's a little bit mental way to do this, right? You know, usually how you get information out of infinity structures is you say, an abstract one is known, I'm going to argue most of those things are 0, and then you win. That's not what we're doing here, because we need such precision on our higher products to get those coefficients out. We actually choose a basis for our DGA, we compute M2, we choose our higher homotopies, and we just keep on going until that's kind of really. And if you're kind of daft enough to actually do that, turns out to be quite easy. And it's because the check thing is so small. And that's the only reason you're actually able to say something. And so there's not really that many general morals I can give to this room that we think about infinity structures. But if your DG thing is reasonable, Kardashev algorithm onto these things is actually quite reasonable, and this all falls out. And in particular, I think, just to wrap up, that Franco maybe talked about this last week, but there's various work on this, that again, if in these lambda defs, if the lambda 3s, that line is 0, then the algebra is definitely infinite dimensional, and the curve definitely doesn't contract. And so the only sort of remaining case in some sense is when the top line exists, and you're going through various cases on that. But it's late, I'll stop there. Thank you.